So let's start. It's okay? Yes. Can you hear me? So on behalf of the organizers, I would like to welcome everybody to Strings 2008 conference. This year the conference is co-organized by CERN and the universities of Geneva, Bern, Neuchâtel, and ETH of Zurich. So I would like to call Luis Alvarez-Gomez, who is the ex-division leader of the theory unit of physics department, to welcome.
Okay. Thank you very much. Well, I'm here really to thank our Director of Research, Jos Engelen, and the Director of the University of Geneva, representing all the other institutions in Geneva who provided support, because when we first thought about the idea of having the String Conference in 2008 at CERN, they were very supportive, enthusiastic. They provided funds, they provided this hall and all the CERN facilities to actually have it. Unfortunately, what they did not provide were collisions. We're waiting for collisions to start announcing supersymmetry at the opening of this conference, so we'll have to have intellectual collisions, plenty of good talks and plenty of good questions. So let me call now Professor Engelen to give you, Professor Vaselli, to give you the official welcome. Thank you.
Thank you very much. Ladies and gentlemen, it gives me great pleasure on behalf of the government of the Canton of Geneva, as well as on behalf of the University of Geneva, to welcome you this morning. Switzerland and Geneva in particular are highly fortunate to host one of the foremost scientific institutions in the world, namely CERN, the European Laboratory for Particle Physics. This gives us the exceptional opportunity to participate, even if only modestly, in what is arguably the most exciting of modern adventures, the exploration of the nature of the universe and of its constituents. In this respect, Geneva, like I'm sure all of you, is looking forward with great expectations to the inauguration of the new accelerator, the LHC, and to the results that we all hope it will yield. In this context, CERN, the universities of Geneva and Neuchâtel, and the Swiss Institute of Technology in Zurich have organized this conference, Strings 2008. And thanks to this initiative, Geneva is happy to welcome you. Being host to some 500 of our planet's top experts in the fundamental forces of the physical world is both a privilege and an honor. We hope that you will spend a memorable week in Geneva with respect to the science that you will share, of course, but also with respect to all the other aspects of your time here. During this week, I believe that you should tackle three somewhat different sets of goals. Let me briefly mention them to you in what, in my opinion, is their increasing degree of urgency. First, of course, you will attempt to reconcile quantum mechanics and gravitation, perhaps coming up with what is called, if I'm not mistaken, the theory of everything. Quite a challenge, I must say, and to which a simple biomedical researcher like me cannot contribute much, I'm afraid. Second, you should endeavor to make your discoveries and theories understandable to the public. This is no less a challenge than the first one, but it is at least, if not more, urgent. At a time when science appears to become more and more esoteric, or even more and more adverse, when the interest of the young generations for basic science is waning, as you know, it is critical to share the importance and the excitement of scientific research. Because your field is so fundamental, because it deals with issues that are so central to understanding our own human significance, and more probably our insignificance, you are in a unique position to reach the public. In this respect, I am very grateful that the organizers of this meeting have taken the initiative of a day open to the public this coming Saturday to take place at the University of Geneva. Finally, and in my mind this is perhaps the most important goal you should set for yourselves, you should work for peace. When CERN was first conceived, shortly after the end of World War II, one of its goals was to contribute to peace. By bringing scientists from many different countries to work together on common scientific projects, it was hoped that this would help generate a culture of collaboration rather than of conflict. The success of CERN rests in a significant way on this vision. Today, unfortunately, we witness again tanks driving across borders and politicians flexing muscles. This could once again be a harbinger to a tragedy. It is our responsibility as academics and scientists to remind politicians that there is much more to be gained by working together to solve the most difficult issues, like that of the nature of the universe, than by menace and by aggression. I sincerely hope that the achievements of this highly international group of some of the world's best minds, as assembled here this morning, as assembled this week in Geneva, will be a live testimony to this vision. It is often said that there is a spirit of Geneva, un esprit de Genève, we say. This spirit impacts on politics and on peace, as well as on science. It is my deep hope that during this week you will not only benefit from, but also contribute to this spirit. I wish you a most productive meeting on all of those issues.
So, thank you very much. I'd like now to call Josh Engelen, who is the Chief Scientific Officer of CERN.
Thank you. Thank you very much. I only have very little to add to what the rector said. It is also a great pleasure for me to welcome you to CERN, the European Laboratory for Particle Physics. And as you know, and as Louis already alluded to, these are very exciting times for CERN and certainly also for high-energy physics. The Large Hadron Collider is cold. That means that 33,000 tons of cold mass have been cooled down to a temperature of 1.9 Kelvin. Now, trivial as that may sound, I can assure you it is not. And getting it cold is one thing, but keeping it there is another. Beam has been injected very recently, about a week ago, in 1 octant. Went around 1 octant, more than 3 kilometers at the first shot. That means that things are prepared, have been prepared really very well. And as I'm sure you know, we want to establish circulating beams by the 10th of September. That is frighteningly precise, that date. The experimental setups around the machine are also ready, or will soon be. And they will be ready to take data. And after an absence of 8 years at the energy frontier, CERN will be back. And that is also very important for us and for European high-energy physics and for high-energy physics at large. I am very grateful to the organizers of the conference to have dedicated an afternoon to the LHC. You will hear about the machine of the person who built it, so to speak. Of course, he didn't do it alone, but he was there from the very beginning, and he has led the project sometimes through difficult years, and he will tell you where we are now. And then I'll have the privilege to tell you something about the technical aspects of the experiments, and the young scientist will then tell you about the physics prospects. Now, whether or not the physics results will shed any light on string theory, or whether string theory will shed any light on these physics results, that remains to be seen. I hope you will take an interest in the LHC data anyway, and some of you might find in them a source of inspiration for your own research. Finally, more than just a laboratory for experimental high-energy physics, CERN wants to be a center of excellence where high-energy physicists, astroparticle physicists, cosmologists, string theorists meet and discuss in an inspiring atmosphere, in a peaceful atmosphere as well. I wish you many confusing and many enlightening discussions, a lot of peace, and a very good and successful conference. Thank you very much.
Thank you very much. So before start, a few things. The conference is webcasted in the council chamber. If someday there are too many people, you can follow the conference from the council chamber, which is across. The headphones work all the time. If you have difficulties to hear, you can use them. However, the microphones do not. They work only during the question sessions. and there can be only 3 people who can talk at the same time. I mean, they can have opened the microphone at the same time. So do not switch the button if the chairman does not give you the ask you to ask the question. So we can start. The first speaker will be Gabriele Veneziano. As you know, this year the conference coincides with 40 years that Gabriele wrote a famous paper on dual amplitudes. So it's a pleasure for us, who is among us, and he will give the first talk of the conference.
Thank you. And view? View, no? View, no? Okay. Let's see, this is also to change transparency? No. Okay. The other one looks better. Okay, I wish to thank the organizers for inviting me. It's for me a great pleasure and also, of course, an honor to open up this String 2008 conference. And the subject of the talk will be 40 years of high-energy string collisions, a subject which has been dear to my heart for, well, most of the time during my career. I think it's appropriate also because, as it was just recalled by Ignatius, this is also 40 years of string theory, in the sense that really day by day, almost day by day, 40 years ago, a CERN preprint was submitted to Nuovo Cimento on 29th of July and published in a record short time on the issue of 1st of September in the then prestigious journal Nuovo Cimento. Now, at that time I was labeled as CERN Geneva. Actually, I was here a little bit accidentally, I could almost say. So I was actually on leave of absence from the Weizmann Institute of Science, where I had recently obtained my PhD, and I was on the way to MIT for my first postdoc, and CERN looked a very nice place in between for a stopover in the summer. So this was exactly 40 years ago. Now, I thought originally of giving a rather historical overview of the subject, but when I realized I had roughly half an hour time at my disposal, I decided to trim parts of it, and finally I decided in favor of physics rather than in favor of history. So the outline of my talk will be like this. I will talk about high-energy string collisions 40 years ago, but very briefly, about the same subject 20 years ago briefly, and about recent developments for as long as the chairman allows. So 40 years ago, there was actually no strings attached to the problem. We were talking about hadronic high-energy collisions, where by high energy we meant a few GeV collisions. These are pictures which go back to actually 1968 at the Weizmann Institute, and also at a kibbutz between Tel Aviv and Haifa. I don't know if you recognize some of the characters in the picture. This ARVV stands for Ademollo, Rubinstein, Virasoro, and myself. I can tell you that Ademollo is not in the picture. You have to figure out whom the other people are. I think Ademollo actually shot this picture. He was visiting the Weizmann Institute in '67. So at that time, as I said, we were interested in high energy, meaning a few GeV collisions, and there was a question of how to reconcile a description of these collisions through the formation of resonances in the S channel and exchanges of regepoles in the T channel, and there was an analytic question to sum or not to sum. And Dolan, Horn, and Schmidt in '67 gave the correct, i.e. negative answer to that question. You should not sum. And out of that idea came the dual resonance model with an essential ingredient, linear Regge trajectories. This was perhaps a first, or perhaps the second, missed hint of an underlying string. A linear Regge trajectory means dj dm square is a constant, but dj dm square is a length divided by an energy, which is the inverse of a string tension, and note that there is no Planck constant involved in this relation. So this is really a classical string description of a string. And the second missed hint probably was the duality diagrams, which were around at the time, which, I mean, they didn't have these wiggly lines in there, but if you add them, you can see strings through the diagram. You see, so this was really very short. 20 years later, that theory of strong interaction had been abandoned in favor of QCD. QCD was well established. The dual resonance model had become string theory, and they were reinterpreted as a theory of everything, so-called, in particular, as a theory of quantum gravity. And I want to stress that there too, the good high energy behavior of string theory was very essential in making the connection to quantum gravity, because this is presumably what cures the ultraviolet problems of gravity. To do so, a huge rescaling was needed. This constant alpha prime was rescaled by 38 orders of magnitude, and a consequent fundamental length of the theory by 19. So from the GeV scale to the Planck scale. Now, high energy, therefore, in that new context meant trans-Planckian energy. I will use TPE for short. And one would have imagined that at those energies, some semi-classical analysis should be reliable and reproduce general relativity expectations. But what was noticed is that the naive tree level turned out to be bad. So usually you associate semi-classical physics to tree-level amplitudes, but that didn't work out in a naive way. At tree-level, partial wave unitarity was violated at trans-Planckian energy, and fixed angle scattering was too much suppressed with respect to the expectations from general relativity. So the questions were, can loops come to the rescue, and if loops come to the rescue, is a semi-classical approximation still meaningful or useful? We will see that the answer to both questions are, at least tentatively, yes, yes, and in a rather subtle way. Now, what are these general relativity expectations? There are several general relativity expectations, but let me concentrate on those which are based on the construction of closed trap surfaces as a criterion for gravitational collapse, which is one of the problems we would like to address in this new high energy regime. Now, of course, if you want to know everything about closed trap surface and black holes, you have to read this recent paper by Christodoulou, but it's 594 pages long, and you have to wait until the last chapter to find the result. So instead of doing that, we'll move to our specific problem of the collisions, for which, by the way, the criteria of Christodoulou are not so useful, because in a high energy collision, the energy is concentrated in very thin cones along very specific direction, and this is a case in which the criterion that Christodoulou gives are not so useful. Now, if you take point-particle collisions at zero impact parameter, namely head-on, then Penrose had an old argument that more than, say, 71% of the incoming energy should collapse into a black hole at very high energy, much higher than the Planck scale. And more recent results, in particular numerical results by Pretorius, show that in fact something like 86% should collapse. If you go to non-zero impact parameter, then you can try to understand at which critical value of the impact parameter you do start forming a black hole. And Erdy and Giddings, in a nice paper a few years ago, gave a lower bound, an upper bound on the ratio of R over B, critical, of 1.25 in 4 dimensions, where R throughout the paper will be defined as 2 times the Newton constant times the center of mass energy. Sometimes this R will carry a label S for Schwarzschild. It's the same thing, okay? Just I was a bit lazy changing everywhere. Now, if instead of colliding point particles you collide extended sources, then the role of the impact parameter is played also by the size of the beam. This is maybe relevant also for the collider. And after some qualitative argument of Husserl, using the method of Erdy and Giddings, Kolprat and myself some years ago established some criteria. Again, these are only sufficiency criteria. I mean, the fact that you are not able to construct a closed trap surface doesn't mean that there is no closed trap surface. So these are only sufficiency criteria. We arrived at the conclusion that R over L, for instance, this is an example for the central collision of 2 homogeneous beams of radius L, R over L critical should be less than 1 in D equal 4. And we will see a more general criterion in a moment, I mean towards the end of the talk. Now, in string theory, what happens is that the string length parameter, L string, plays the role of the beam size. So actually the two particle collision of 2 strings have 3 length scales associated with it: the impact parameter, the Schwarzschild radius, which is the energy in Planck units, and the string length. And the existence of these 3 scales defines 3 broadband regimes in trans-Planckian superstring scattering, depending on which scales dominates over the other. You have a regime of small angle scattering where the impact parameter is much bigger than R and LS. You have a large angle scattering region where B is of the order of R, both bigger than the string length. You can go into a collapse region, as we said a moment ago, when B and LS are smaller than the Schwarzschild radius. And there is a stringy regime as well, where the string size dominates actually over the Schwarzschild radius and the impact parameter. So these 3 regimes are indicated schematically in this plot, where I have the Schwarzschild radius and the impact parameter, and there is a string length scale. Note that we take the string coupling G string very small, so that, according to the usual formula, the Planck length is much smaller than the string length. And note here that there is a so-called threshold energy for black hole production, which is given by the string scale over 2 powers of the string coupling. This is the energy at which the radius, the Schwarzschild radius, coincides with the string length. And of course, the Schwarzschild radius is LP at E equal MP. Okay, now the expectations from what I told you about classical general relativity is that there is some kind of critical line, which is this red line, which separates the region of scattering from the region of black hole formation. Black hole formation doesn't mean, again, that all the energy collapses, but at least some of it collapses. And so it would be very interesting to study what happens near or beyond this critical line, but unfortunately things are easy in this way and become very complicated as we try to penetrate into this black hole region. Now, high energy does help, very high energy. There are general arguments as well as string loop calculation which suggest that in a trans-Planckian energy, very much above the Planck scale, the S matrix takes a semi-classical form with corrections. And the S matrix is given in terms of a classical action. And the classical action in d dimensions takes the form indicated here, where CD is some well-defined number, which depends on the number of dimensions, some solid angle, and so on. Then there is 1 plus various type of corrections. And there are so-called classical corrections, which we'll discuss at the end, and some string size corrections, which go like the string length divided by the input parameter. And then we will neglect throughout the talk other quantum corrections which scale like the Planck length. Now, for instance, this leading term is a so-called leading iconal approximation and corresponds to the exchange of gravitons between the two fast particles with cross ladders also included. Okay, they are not drawn here. Now, you have to realize one important thing, and this is that this part of the action is real, but the corrections can contain imaginary parts. So when there are imaginary contributions to the action, those may be much more than just corrections because they give the leading term in the absorption of the elastic amplitude, okay? Because this first term just gives elastic scattering. The corrections may give inelastic channels and the main contribution to absorptions. Let me make 2 examples of string corrections. The classical corrections controlled by the ratio R over B will be discussed later. So here are my strings colliding, and this is a 2-loop diagram. In this 2-loop diagram you can recognize 3 gravitons which are exchanged. These are the red closed strings. But then you can also recognize the existence of what we can call diffractively excited strings, the yellow ones. You see you have the 2 incoming particles, they exchange a, well, what turns out to be a graviton, and they get excited to some excited states. But then there is also this big blue closed string, and this is a heavy string produced in the S channel, which also contributes to the imaginary part of the classical action. We call this cut graviregions, gravitons which are regiized in string theory. And these are the exchanged graviregions. Now, let me discuss, so the existence of these corrections, since they are important for the absorption, complicates the previous diagrams, and there are new regions which appear in our parameter space. I will not go too much into the details, but just list more or less the different regimes which are of increasing difficulty in dealing with. There is this easy small angle elastic scattering for which the leading icon works. There is a small angle inelastic scattering. There are 3 kinds of inelasticities that can be taken into account. One is the string excitation. I will describe it in a moment. Second, these are where these yellow strings which get diffractively excited. There is string formation in the S channel, and then there are graviton, rather massless particle emission. Bremsstrahlung type diagrams. Then we have large angle scattering, which is necessarily very inelastic, and finally the most difficult region will be the one of classical collapse. So if you want, the previous diagram gets a bit more complicated. I don't have the time to go into the details, but this is in a log-log plot at the various regions of this parameter space, leading iconal, diffractive string excitation to the right of this blue line, S-channel production of strings in this region, graviton radiation, Bremsstrahlung to the right of this green line. In this band there will be large angle scattering, and below this second red line there will be black hole production and evaporation. So the question is, how do you describe all these regimes? So let me start with the easiest one, which is small angle elastic scattering, for which the leading iconal approximation is valid. So we neglect everything else, we just keep this term. We keep this term and we get an S matrix which satisfies elastic unitarity. Why? Because this takes the form of S to the 2I delta. Delta has this real part and has a vanishingly small imaginary part, because we are in the region of impact parameters much bigger than the string length, and therefore we can neglect the imaginary part. So we take that leading iconal result, and what we can do is we can go over from impact parameter to scattering angle by standard Fourier transform, and we find that the amplitude is dominated by a saddle point in impact parameter, which lies at this position, B saddle to the d minus 3 equal g square root of s divided by theta, or you can write that theta is r divided by b to the d minus 3. And this corresponds precisely to the relation with all the coefficients, which I didn't write down here. They are numerical coefficients. It coincides precisely with a relation between impact parameter and diffraction angle in the so-called Eichelburg-Sechsel metric, which is generated by a relativistic point particle of energy E. So each string or each particle behaves as if it moves in the metric, non-trivial metric, produced by the other particle which comes against it. And this is precisely the relation that one should have. Now, however, here comes the first string effect. Unlike a point particle, when a string moves in an Eichelburg-Sechsel metric, it suffers tidal forces. Okay, famous tidal forces of gravity, as a result of its finite size. I think this was first pointed out by Steve Giddings a couple of years ago. It's, if you want, the gravitational counterpart to diffractive excitation. We called them in the old days diffractively excitation, but I think this tidal force is it's a very nice way to think about it. And the question is, where does this phenomenon kick in? And the tidal force argument, originally due to Giddings, I tried to understand this argument and re-elaborated it a little bit, is quite amusing. You see, what happens is that since a string is an extended object, different parts of the string hit the shock wave at different impact parameter. So they are not all deflected in the same way. So remember, the deflection angle, according to our formula and to Einstein, is GE divided by b to the d minus 3. But since the various pieces of the string are at different b, there will be a spread in the angular deflection, which will be the derivative of this object with respect to b times the string size, which is what happens here. But now, this angular spread provides an invariant mass. You see, if the string was deflected as a whole, it will keep its mass. But if it starts to be spread in deflected in different directions, then it's like a beam of massless particle with an angular opening. The mass they acquire is proportional to the energy times the spread of the angle. the angular spread. So if you use this formula, you get immediately G times S, which is nice because it becomes relativistic invariant, times this. And it will be the same for the two things as it should be by symmetry. Now, the strings get excited if the mass they acquire as a result of the tidal forces equals the string scale. And when you put all this in, you find indeed that this phenomenon kicks in at the impact parameter, which is given by this formula, which is precisely the result we obtained in 87. The other interesting thing is that the elastic cross-section is absorbed as a result of this opening up of new channels, and it's depressed, is absorbed as the exponential of the entropy of a string of mass m. M equal m1 equal m2. You know the entropy of a string of mass m is m over m string. Actually, even the coefficient works out precisely, and so we get this nice relation between the suppression of the elastic channel and the entropy of the diffractively produced strings. So this is the first string effect which I wanted to explain in a little detail. The other string effect is the formation of this S-channel, heavy S-channel strings, and that happens when you go to impact parameter, to this region in which impact parameter and Schwarzschild radius are small compared to the string length. Then the imaginary part of delta, which I neglected previously, is now important. The elastic amplitude is suppressed by e to the minus 2 imaginary delta. The elastic cross-section is the square of this, so minus 4 in delta. And this is the suppression you get for the elastic amplitude. It goes like e to the minus s over a scale, m star square, which happens to be the geometric mean between the string scale and the threshold scale for black hole production. In particular, if you go to an energy corresponding to the threshold, to the supposed threshold of black hole production, this exponential becomes e to the minus 1 over g squared, which again is nothing but the exponential of minus an entropy, and this time is the entropy of a string hole, which is my favorite name for a string of mass E threshold, which, as you know, is the value of the mass at which a string entropy equals the Bekenstein-Hawking entropy. So also in this case, the elastic cross-section is suppressed by an entropy factor, and we will see a similar result later on. Another interesting thing is that the number of these heavy strings that you form grows like the second power of the energy, like S. In fact, this is nothing but exponential of minus the average number. Is like a Poisson distribution. And therefore, if you compute the energy, the average energy associated with these produced strings, it will go down with energy, because you have to share the total energy by the number of these strings. So they actually become lighter and lighter and less energetic. And the amazing result you find is that if you define this average energy like an average temperature of the final state, that temperature goes inversely proportional to the incoming energy. So this is a very characteristic thing of gravity entering in the problem, a huge increase of the multiplicity and a corresponding reduction in the energy. So many soft particles. In fact, if you draw the diagram of the average energy of these cut gravity regions, it goes like e to the minus 1, and you can see that up to a numerical factor that we cannot compute, when we approach this threshold energy for black hole production, this energy coincides with the expected Hawking temperature, and at least in d dimensions, this e to the minus 1 law should continue, while it should change a little bit. 3 minutes. Wow. Oh, I thought you gave me the extra time we gained. Now we come to today's work. Now today we have additional phenomenological motivations for these studies. We may expect to find signatures of string or quantum gravity at the LHC. Well, not in any circumstance, but at least in various models in which we can lower the true quantum gravity scale to the TeV scale. And my chairman was one of the first to pioneer the idea that with extra dimensions you can lower the scale of quantum gravity even down to the TeV scale. But we have to stress that in the most optimistic situation, the LHC will be very marginal for producing black holes, let alone semi-classical ones. So to find precursors of black hole behavior like the ones I just illustrated, even below the expected production threshold, I think it's very, very important. Because you may see signals that something is boiling. Now, there is an additional theoretical motivation for this gain, which is related to the famous ADS-CFT correspondence. There are hopes now that a suitable generalization of ADS-CFT may lead to a good string model for QCD, if you want, going back to the old game. And there were infrared problems affecting the early attempts to describe high-energy soft hadronic interaction, now should be absent. There have been very interesting recent developments, like models for the soft Pomeron and connection with gravitational processes in ADS, many authors, and then also work on the hard Pomeron and connection between parton saturation and the critical collapse a la Choptic. So maybe the old program can be revived. Now, how do we approach the problem of these classical corrections to the leading iconal? So we are now discussing, now we are neglecting, unfortunately we are not able yet to do everything together, so let's neglect these effects and let's for the moment concentrate on these other effects, but actually everything should be done together. So we can do this to study graviton emission perturbatively, or we can even go to these regions of large angle or even of collapse by trying to resum, not just keep the leading order, but try to resum these classical corrections. From here on, I'm in d equal 4. And the classical corrections are characterized by the absence of H bar, but not surprisingly they are related to tree diagrams, but not naive tree diagrams. Naive tree diagrams, once the coupling to the external energetic particles is replaced by classical sources. So these are the diagrams which should dominate the classical corrections. It's technically speaking loop diagrams, but there is a tree here in the middle. And you can do some power counting to convince yourself that indeed this diagram scale in the right way to give the corrections of the right order. This is the leading diagram. You see two gravitons upstairs, two gravitons downstairs, which reinteract in a tree diagram. We call it the H diagram, and it scales like an extra 2 powers of R over B. Now, the nice thing is that there is a simple 2-dimensional effective action which generates all these leading tree diagrams, and it contains 3 fields, and it's like this. It's quite simple, however it contains high derivative terms, okay, perhaps because it's a theory of gravity. And the equations of motion can be written down. It's quite elegant. Now, the semi-classical approximation will correspond to solving these equations of motion, computing the classical action on the solution. It's too hard for analytic study, but as we will see in a moment, if Chairman allows, it's numerically doable. On the other hand, we can do something analytic if we concentrate on the case of axisymmetric collisions. Now, for particle-particle collisions, axisymmetric collision means zero impact parameter. You can close your eyes and do it, but it's not really physically very reliable. So what we thought about was to do a central beam-beam collision, namely extended sources, which hit each other in a central way, so with an axial symmetry. And then the situation is simpler and can be done analytically, or almost analytically. I mean, analytically I include to solve some ordinary differential equation with Mathematica. Okay, for me this is almost analytic. The nice thing is that in this particular case, the closed trap surface criteria are very simple. The numerical results should be forthcoming if you see recent talks by Choptwick and Pretorius. There are two major simplifications from our point of view. The partial differential equations become ordinary differential equation, and there was something I didn't mention about the infrared singular polarization, which is absent. Now, how do the equations look like? So let's not stare too much at the details given the time. They reduce to one second order ordinary differential equation, which is written here in terms of some auxiliary quantity. Here t is actually r squared, the distance from the symmetry axis, with boundary conditions which are of the Sturm-Liouville type, because they fix this rho to be 0 at 0 and to have unit derivative at infinity. So you fix two boundaries, one at infinity, boundary condition one at infinity, one at 0, in terms of this auxiliary quantity, which is related to the emitted graviton field. Now, I told you that the collapse criteria become very simple. In fact, back in this paper with Kolprath, we proved this sufficiency criterion. If there is an R such that R1, R2 is equal to R squared, R1, R2, which are defined here, is the energy in each beam or in each source below a distance R times G Newton, okay? So these are length scales. You multiply the two. If the product of these two energies hits this value at some point, then we can construct a closed trap surface and expect a black hole to form. And with Wozniak, we proved the theorem, is here, that whenever this criterion holds, actually it's sufficient to have this slightly weaker criterion. The Amati, Ciafaloni, Veneziano field equations do not admit regular real solutions. So it seems that this collapse criterion implies that the absence of real solutions, which we interpret also as a signature of black hole formation. Now, by the way, I have the luck now that I'm in Collège de France to have some very good mathematicians around, so I asked the advice of Pierre-Louis Lyon, who is a field medalist, and he very kindly looked through this equation and so on, provided some rigorous argument for certain things, and even gave me this result. Now it's a sufficient criteria for dispersion. Dispersion is the opposite of collapse, okay? Everything that comes in comes out. And so for the moment we have these two curves. These R1, R2 characterize the two beams. And if this function touches anywhere this red curve or goes beyond it, you have collapse. If it stays all the time below this green curve, then there is dispersion. But clearly there is room for improvement because many curves do neither one nor the other. So in general, you have to solve the problem numerically. I have 3 examples. One can be done entirely analytically, and this is the collision of a point particle against a ring of size b. There, unfortunately, the chairman tells me there is no time. You can do everything analytically. You end up with a cubic equation, and the cubic equation has positive real solutions only if b is bigger than this BC, and that means that BC is 1.61 R against the CTS bound, which was BC bigger than R. So this is an analogy which I will skip. Then there are 2 more examples, and we can all the time compare the CTS criterion, which is very simple, with the numerical results, and there is agreement. As I told you, you can go back to the 2-particle collision problem in the non-axisymmetric situation. You can do it numerically. This was done by Marchesini and Onofri. They found a B critical of 2.28 R against the lower bound of Erdi and Giddings of 0.8 R. And okay, then you can continue and study other things. What I wanted to mention is that, again, from the study of this process, it turns out that while for B much bigger than the Schwarzschild radius, gravitons are produced at small angles, at large rapidities, as you go towards this critical value, their distribution becomes more and more spherical, again with an average number which goes quadratical in energy, and therefore with characteristic energy which goes down with incoming energy. And then as we go beyond BC, we develop a new imaginary part on top of the one due to Bremsstrahlung, and we may try to interpret this as a result of a black hole formation. And if, again, we try to identify this extra elastic suppression as due to some entropy factor, then we have to conclude that what we form just above the critical point is a black hole whose mass goes to 0 at the critical point and grows like this fractional power of the distance from the critical point, which would mean a Chopwick exponent of 0.75. Well, his value in the probability studies is more like half of that. Okay, I have only the conclusion, may I? Okay. So, let me summarize and conclude. Gedanken high energy collisions, because we have to remember that even in the old days of low energy collisions, the reaction we used was pi goes to pi omega, hardly something you can do experimentally. So, but they have played an important role in the early developments of string theory. Now, after the 1984 revolution, trans-Planckian energy collision may well play a similar role for understanding whether and how quantum mechanics and general relativity are mutually compatible in a string theory framework. We can do superstring theory in flat space-time or in other consistent background like ADS, and they offer a concrete framework where the quantum scattering problem is well posed. Now you have to solve it. The problem simplifies if we go to trans-Planckian energy, because we can justify a suitable semi-classical approximation. And what we have done was to consider these 3 regimes, which I will remind you: large impact parameter, the string size dominated regime, and finally, this last part of my talk was on the strong gravity or large Schwarzschild radius regime, where we can use an effective action approach which can be tested. We found critical points or critical lines in general which match well the closed trap surface based GR criteria. We find that as we approach these critical lines, the final state, start to resemble a Hawking-like spectrum with a fast growth of multiplicity and a related softening of the final state. And then progress was made towards constructing a unitary S matrix, which of course is important. I didn't mention this, but it was obvious, this famous information paradox problem. I mean, do we have loss of information when a black hole is formed and then evaporates? Well, much more work remains to be done, but I think that finally an understanding of the quantum analog, or what replaces gravitational collapse in string theory, does no longer look completely out of reach. Give me another 20 years and we'll see. Thank you.
So, we have time for a couple of questions. No question? Okay. Then thank Gabriele again. And before the break, let me just make some announcements. So today will be after the conference at 6, the reception at UN. You have all the information in your bags.